our capacitive and our inductive sensors. And we've already talked a little bit about capacitive sensors, what do they do? Hey, they can be defined. Inductive sensors only sense what? Hold on, guys. My wife's calling. So when we get into these solid state sensors or these capacitive inductive sensors, we have two forms that we can buy. We can buy what they refer to as an unshielded and a shielded. Y'all can see the difference. So what's the unshielded? Well, there's a blue one. Yeah, there's a lot of the sensor exposed. And then we have a shielded. So notice here the sensor and the mounting screws are basically flush. Now what would you think, what difference would that make? Which one? Yeah, so the shielded would be more selective. So these guys are designed to be mounted flush, right? You understand? So you'd see these come up and mount flush. The capacitive, the unshielded would have a bigger range, right? You understand? That makes sense? So yeah, the shielded would be more selective. The unshielded would have a broader range. This is basically the way these things work. So what we have to do to get a capacitor is we have to have two conductors. And sometimes we get capacitors we don't want, and sometimes we have capacitors we do want. So what we do is we have two conductors, and in between them we have an insulator. And then we have two conductors like this. So we have two, they call them plates, separated by some type of insulator, and then we attach conductors. Now what happens is these two plates are extremely close together and they react to each other electrostatically. So that means if I come over here and put a positive on this side, what this thing right here is so narrow, what do you think it's going to suck onto this plate right here? It's going to pull in negatives, right? You understand? Just by the electrostatic field. And of course, if I come over here and put a positive on this side and put a negative on that side, then it's going to discharge and then charge back up to the other direction. We can use these things in DC. DC, what happens is we come over here and we put DC on this thing, and I'm going to put a resistor over here on purpose. Okay. And then I put a DC battery right here, and then I'm going to put a switch. Is when I close that switch, and I put that positive on this side and that negative on that side, the bucket's empty. So what's going to happen? It's going to start rushing in real fast. So the way this starts off with is if I have 10 volts right here, as soon as I close that switch, that capacitor drops 0 and that resistor drops 10 volts. And then what happens when this charges up to 2 volts, then this guy here is going to drop what? 8. Well, as soon as the resistor drops 8 volts, then less current flows through it, right? You understand? Because we can calculate the current. So if I say I is equal to V over R, well, what happens is V went down across the resistor, current went down, so the capacitor charges slower. Then it would come up here. If this goes to 5 volts, and this right here be 5 volts, the capacitor charges slower, right? You understand? When this over here gets up to 10 volts, it charges up to 10 volts, and the current in the circuit stops. So if we looked at a charge curve on a capacitor with DC, it charges like this. And then once it's charged, then there's no current flow. So when we originally closed that switch, it acts like a short. And then when it finished charges, it acts like an open, right? You understand? Now, if I put AC on this thing, it just acts like two buckets. and then I'd come over here and I'm putting an AC right here, and I'm gonna put a resistor. And what's going to happen is that when the polarity goes like this and this, what's going to happen? This side's going to charge positive, this side's going to charge negative, and when it swaps, what's going to happen? It's just going to turn around, right? So technically, we say in a DC circuit, a capacitor acts like an open, because eventually it's going to charge up and it's going to get an open. By the way, we use this guy for time. This charge time is pretty proportional. They call it an RC time constant, where time is equal to R times C, but it's not fully charged. This is like 63%. And it's pretty accurate. Then what we do is if I kept charging it, and then another time constant, it would charge up and charge up, but it fully charges in about 5 time constants. So all we have to do to figure out how long it takes to fully charge is just multiply whatever resistor I use by the size of the capacitor times 5, and that'll give us the full. We use these guys all the time, just for basic timers. So if you got a motion detector at your house and you walk out there and it turns on and you walk off, I'm almost guaranteed the time it takes is done by just a little RC time constant. So we use these for timers a lot in DC. But if I put AC on it, it passes the AC. But the slower it charges, the slower the frequency, the more it acts like DC, right? You understand? The higher it charges, the faster it charges. So basically, it varies its opposition with frequency. So when we buy capacitors, we buy them by their capacity. So that's what C stands for. And it's in farads. So we buy so many of 50 microfarad, or they usually come in microfarads and picofarads. So they skip over nanofarads. And then F stands for what? Frequency. And then this right here is just a constant, 2 pi. We use 6.28 usually. And what this does is this gives me the AC opposition of the capacitor. So the higher the frequency, the less opposition these things have. But there is no current flow through them. So they do no work. They don't get hot. But they do appear to do work, right? You understand? So in AC, so if I can come up here, what would you think would determine the amount of capacitance? Size of the plates. So the bigger the plates are, the more capacitance they have. So the C would go up. What else would change the amount of capacitance? The material between the plates, what type of insulators that we use inside there. So we have different types of insulators. And what would be the next one? You've had AC. How close they get together. The closer we can get the plates together, the more they interact. So it would go up. So we got 3 things. And so we can buy variable capacitors. All we can do is we can either adjust the size of the plates, and normally they do it by an overlap. So they'll have 2 plates, and the capacitor only exists where they overlap, right? You understand that? So you'll see these things that we turn and they'll overlap, or we literally change the distance between the plates. So we can have variable capacitors or whatever. But so what would you think a capacitive sensor do? Which one of these things would we change? If I'm going to make a capacitive sensor, which one of those things would I change? I could change the distance between the plates. That would be a physical adjustment, right? I could change the size of the plates. That would be a physical adjustment. So my capacitive sensor can't be changing those. What am I changing? Not the frequency. I mean, it don't sense frequency. How is this guy right here going to generate a frequency? Right? You understand? So what do you think these things change? Now, in inductive sensors, they do. It's got to change. It's got to change what? It's got to change the dielectric. Somehow we're changing what we call the dielectric constant of the wall of the insulator. And that's what we do. So what I have here, I think I forgot my camera. No, it's running, right? I just got to switch over to the right one now. I'll get in sync here. Well, let's switch over to this. I don't see it. this listed now. Here we go. So what I have here is I have a AC signal. So we got to put AC on it. If I put DC on it, it just act like an open, right? So we have this device right here. I need to rechange this thing too. So this is called a function generator. And what this does is this generates AC waveforms for us. We can generate 3 different waveforms. We can generate a sine wave, a pulse waveform, or a triangle wave. So I've got it on sine wave. I can use this to adjust my output, and then this right here I can use to adjust my frequency. Right now I've got roughly about 4 kilohertz. Now what I've done is this is the connection for my function generator, and then this is an oscilloscope. So what an oscilloscope does is it shows you exactly what's there. So it's not like a meter. A meter gives you an average of everything. Oscilloscope shows you exactly what's there relative to time. So what I've got is this right here is the output of my function generator. This right here is the input to my oscilloscope, and you notice these suckers are not even touching. Not even touching. But when I come here and look at my oscilloscope, it's picking up a signal. So how's that signal getting there? Well, it's getting there through this electrostatic field, right? So right now, this is my insulator, right? You understand? And then these are my 2 plates. And these things are not physically touching, which is pretty neat. So I'm actually sending this through nothing, right? You understand that? So what we're going to do is I'm just going to come over here, and I'm going to just come over here and put my hand on this thing. And we'll see if the output changes. Can y'all see it actually change? Okay, I mean, I could come over here and put my mouse on there. It's hard to see, but you'd actually see it change. I could come over and put this tape on there, and you'd actually see it change. So what I'm changing is I'm changing what we call the dielectric constant of the capacitor. So capacitive sensors are real easy. So all we do on a capacitive sensor is we create the field a little different. What they do is they come over here, and the 2 plates are mounted opposite of each other, but they're right beside each other, and they have a little tiny gap. So these guys are actually generating a field that looks like this, right? You understand? And then when I get anything in there, what am I changing? Well, I'm changing the dielectric constant between the 2 plates. And this is the way a capacitive sensor works. But what's nice about a capacitive sensor, they can sense what? Just about anything. Now, the inductive sensor works a little different. The inductive sensor works off what we call inductance. And unfortunately, I didn't have time to hook it up. Now, what I want you to notice is the formula for y'all don't need to know this formula. Y'all not writing in this formula, right? I mean, this is nothing in this class. You'll learn more about these in AC. You know. It won't let me erase this. Huh? Yeah, so the frequency goes up, and it's just like a pump. You know, the faster you run the pump, the faster the water moves. So in AC, we're just running that pump back and forth, back and forth, The faster you run it, you're just charging those things faster. You're filling up the buckets, you're swapping around faster. And so if the water flow goes up, then in AC, that's the current going up. So the higher the frequency, the less opposition that capacitor shows. And what we have to understand is any piece of wire, if we get 2 conductors that are close together and we put AC on those things, what did we just make? We made a capacitor. This don't affect us on low impedance circuits like power grids, because there's so much current that we can't really do. It don't affect it. But you get into communication cables, these high impedance circuits, right? You understand they're not designed to handle a lot of current. They're designed to send signals. Then these we call them stray capacitors. They can become very, very critical in those circuits. And we take advantage of that too, by the way. So here's 1/2. Now, when we look at the formula for An inductor, it's not one over, right? You understand that? So what an inductor is, it's just a bunch of loops of wire. That's all it is. And that's the symbol for it, by the way. And what happens is when we put a current flow through this, when that magnetic field from this one transfers into that one, it creates an opposition that's in the opposite direction. Whether you understand it, it's not really important in this class. But what happens with inductors is frequency goes up, its opposition goes up. If frequency goes down, its opposition goes down. If you put DC on it, it acts like a long piece of wire. You know, I'll try to find that and show you. We got a spool of wire that I roll out. It's probably around 30, 40 feet long, and I'll put it out like a wire, and I'll hook it up. It looks like nothing happens, and I'll start wrapping it around my hand. And we'll put a resistor in series, and you'll see the voltage drop across the inductor goes up, and the voltage drop across the resistor goes down, which is pretty neat. But what we do here, what determines how much inductance we have? So this guy right here is in a unit called Henrys. What determines that is basically how close we can get these wires together. We call it magnetic coupling, right? How close we can get them together, the number of loops that we have, right? And then what you put in the center of these things, or what you couple the magnetic field with. So a lot of inductors will have a ferrous core through it. It'll be where they take like iron dust and something and glue it together. And they use that as a core. Sometimes they use ceramic, sometimes they use air. But if I can come up here and put something in close to this thing, a piece of metal in close to this thing, then what's going to happen? It's going to change this right here. It's going to change L. Now we can't simulate this because it's a little harder. We'd have to have an oscillator circuit on this one. But what happens is the closer that metal gets to that, the more L we have. And the more L we have, the more drop we have across the thing, right? Does that make sense? But this takes something that's going to concentrate the magnetic field, which is going to take some type of what? Some type of metal, right? So inductive sensors only sense what? Metals, right? But they look basically the same. So we have two types. We have what? Shielded and unshielded. They look identical to each other. So this is something you have to keep in mind. You know, well, go in there and get me one of these. They go trucking in there and they say, well, that looks like it, right? And, they give you an inductive sensor instead of a capacitor or vice versa. That could cause you a lot of problems. So this is where keeping those things separated and also learning your part numbers would become very, very important. Because we call these things are referred to as solid state limit switches. And that's what they're both called because they've been around quite a long time. So anytime you hear a solid state limit switch, that's what they're talking about, but they don't differentiate between capacitive or inductive. Now, normally these guys only have two wires. These things take very, very little voltage to operate. I think if you take the sensors class, we'll find out that these guys here, it takes around about 3 volts to operate. So that means if I come over here and I put in, so what these things usually do is we come over here and I'll have my inductive sensor. I'm trying to remember the symbol of inductor sensor, but we'll do it. Then what they'll do is they'll come over here, and if this right here is a relay coil, there's no power going to it because it literally powers up through the load. So when whatever comes over, so I might have a contact over here. Well, as soon as this closes, this guy here is going to drop about 2 volts, and if I got 24 volts, that still leaves 22 volts to operate the coil, which is still plenty, right? You understand that? So the problem with these solid state limit switches is they drop a voltage. If this was a limit switch and the limit switch was made, how much voltage would it drop? 0, right? You understand that? Unless something's wrong with the switch. Solid state limit switches will drop a voltage, but they operate through the load. That makes sense? But they drop a very little voltage and it always leaves a lot. I think on our AC sensors over there, they drop about 4 volts, but they're AC and it's 120 volts. So if they drop 4 volts, that still leaves, 116 volts to operate the relays and stuff. These guys are going to have 2 wires on them. They'll have 2 wires. So all your photo sensors are going to have at least how many? 3. Your Hall effect's going to have 3, right? These guys will probably have 2 because they operate through the load. They take operate very little current too. I think around in the milliamps, or maybe depends on where it is, but it's in the milliamp range to make these things operate. But we understand inductive sensors only sense what? Metals, right? And then capacitive sensors can be basically designed to gases. We can do gases, liquids, solids. We can do just about anything with those. Well, what's neat is inductors and capacitors cancel each other out. Pretty neat. You'll see why? So one of them, the opposition goes down when frequency goes up, and the other one, they swap around. So let's go back over. So same thing. So any sensor. What's that? A transducer is a transducer. Trans changes, right? So transducer is another name for a sensor. So instead of me saying a through the beam sensor, I could say it's a through the beam transducer. So those two terms are used interchangeably. But distance, we could use to sense distance. We could use to sense speed, kind of like radar, so I could send out a pulse and then it bounces back. I send out another pulse and it comes closer. Then I know that it's moved a certain amount, right? Understand? The reflectivity does depend on the surface that you have, but these guys are usually calibrated, right? We can literally calibrate them and increase the gain. So we can make these things reflect off liquids. So if you went down to the big gasoline farm down there in Pelham, that's gasoline, guys. That's not oil, that's gasoline. And you don't want to put an electric probe down in gasoline. Well, they have ultrasonic sensors up in the top, and they're literally bouncing off the gasoline to do that. So they use ultrasonic sensors for that. But we use these things. We're using ours to, what's ours being used for over there? Well, so it's doing distance. So the way it's set up is it's a range sensor. So on that one, it's that we can set it at we can calibrate it for a low range and an upper range. And then the sensor memorizes that. And as long as it's within that range, it says it's okay. If it's outside that range, it says it's bad. So that's basically where ours are set. And of course, we're not going to go over and look. We've only got one ultrasonic sensor. That's the big one over there. So one of the things that we'll do during the term is we'll calibrate. Well, what we'll do is we'll simulate replacing it. So what we'll do is we'll go over there and we'll take it off, and then you'll put it back on, and then once you put it back on, you'll have to do what? You have to calibrate. So we got the calibration procedure. The other sensors that we have on the line over there is we have pressure sensors. We have what we call a pressure switch. And then we have an analog. So we have these can be analog or they can be digital, right? These guys, they use different techniques. I got my sensor from them. You gotta have a sensor. So this is called a bellows. You can see it's usually made out of metal. So when we come in here and we put pressure in one side, what's it going to do? It's going to expand, right? And of course, what's nice about these could also measure a vacuum. So this is the bellows. Huh? Just bellows. Like it's got its own accordion. This bellows. Well, it all depends on what you put in the scenes. So you imagine, all I got to do is take a motion and convert it over to something. So if I hook the output to a potentiometer, and when it expanded, it would change the potentiometer, that would be an analog sensor. If I was to come up here and put a switch up on top of the bellows, so my bellows is up here, right? And I mount it, so we mount it solid. And then my bellows, I need to draw it upside down. And then my bellows is like this. And then I come up here and put a limit switch up here. Then wherever I set that limit switch up, when it comes up and hits it, then that would be that, right? Or I could put a potentiometer up here, and when it moves up, so we could use like a rack and pinion. And then I could take this and run it into an analog to digital converter, and then I have an adjustment, and then I could determine when it says the pressure is right or the pressure is wrong. What a lot of people don't understand is normally on these pressure sensors and these other sensors, we actually combine two things to come up with a sensor. So that means the bellows itself does not give me an output. All it does is expands or contracts. Then I have to come back and combine it with another sensor, right? You understand, to actually determine whether it's an analog or other sensor. But we usually don't talk about the other sensor. We just use it as one unit, right? Does that make sense? So a lot of our sensors, like the light sensor, so we send out a light beam, it hits something, it bounces back. Well, we already know that it depends on a certain amount of reflection, right? You understand that? So here we're combining it with some type of A to D converter or some types of electronics, like this guy right here. So this is called a Bertillon tube, and these guys have been around since I don't know how long. And these work on the principle when I come up here and let me put this full screen. Wrong thing, Rich. Full screen.
They use out bellows which are used out.
Well, it all depends. Some we have solid state pressure switches that works on a piezoelectric principle, a piezo resistance. So, but what you're going to run into is the older the equipment is, the more likelihood you're going to have stuff like this and not have solid state stuff, right? Like this guy here, this guy's been around for as long as I can remember, even before Rich. This is called a Bertillon tube. And you played around with Bertillon tubes probably at a birthday party. You get those things that's all rolled up, and you put pressure in one side. What do? They unroll, right? You let them go, and they automatically do what? Come back. That's a Bertillon tube. Well, here's this Bertillon tube right here, this piece of metal. And then when I come over here and put pressure down on the end, what's the tube going to do? It's going to do what? It's going to try to straighten out, right? You understand that? Well, all of a sudden, this used to be a mercury switch, and I can set that. So when this thing come up here and hit a certain thing, it did just what? It just switched, right? You understand? So I could come up here and change this angle right here, and then I could change the angle when the pressure was too big or when the pressure was too low. That makes sense? So this is a Bertillon tube. These guys have been around. They're still used a lot. Very simple concept, right? Huh? Could be air, could be hydraulic. Bertillon tube don't care. All the Bertillon tube does is it takes a pressure and converts it into a motion. That's all it does. But into a motion. Now, if I want to use that motion digitally, then I've got to add another sensor, like a limit switch or something like that. to give me a 1 and 0 output, or a resistor. I could add a potentiometer. So this guy here could definitely turn a potentiometer knob, right? And then my potentiometer could give me a voltage that was proportional to a pressure. So we can use Burdon tubes in digital, or we can use Burdon tubes in analog. This is a C Burdon tube. They have one they call a helix Burdon tube, where the tube is actually vertical and is in a loop. And then when they put pressure on it, what does it try to do? It tries to come out of the loop. So that would be what they call a helical Burdon tube. We don't have one of those here. Then I have a diaphragm. This is the diaphragm. So this is a diaphragm type. So the pressure would come in to this inlet right here. And then what it does is just pushes the diaphragm out. Right? You understand? This comes out on a rod. Now what used to be mounted out here was a limit switch. So when this thing came out and did what? When it pushed out so far, it would just energize the limit switch. This is a diaphragm. These are still used a lot in HVAC systems to sense when certain things happen. Especially if you got a gas heater. Most of our gas heaters now don't run what we used to call a pilot light. What was a pilot light? We still use them on water heaters, because water heaters are self-energized. They use a thermocouple off that thing to create heat. The HVAC system, though, they use basically a spark plug. I mean, they call it an igniter, but it works just like a spark plug. So they put a real high voltage on there. So what they do is they don't want to turn. So first thing they want to do on those things is they want to purge the chamber, right, where the gas burns. So they'll bring a fan up and they'll blow it on. Well, they want to make sure that fan blows. So what do they use? Well, they use one of these things. And it's in my air conditioner. They got a tube running down from the fan and goes down to one of these. And now it won't ignite unless that fan comes on and purges out the combustion chamber. You don't want to turn on that spark if there's gas in that chamber, right? Because what would it do? It'd blow up. Yeah. So, I mean, these things are still used a lot. These little diaphragms are used a lot. They're very, very cheap, very, over solid state. As soon as you say solid state, you're talking about adding more cost. So these little guys, these are still used a lot because they're very efficient. They've been around a long time. The technology is well understood, right? You understand? Like I said, if you got a gas heater on your house, I almost bet you it's going to have a diaphragm out there that makes sure that purge fan comes up and purges that combustion box before that flame comes on and ignites. And then we have solid state, guys. I think that's on the slide here. So diaphragm, you'll see the diaphragm. The diaphragm is usually put some metal plate, or it might be that. We got bellows, piston. I forgot about piston. We don't have a piston right here, but it's obvious how it works, right? So we come in here, we put pressure on one side. It's going to cause the piston to do what? Push against a spring, and it's going to push it as far until the spring tension equals to the force. And we have solid state too. I don't have solid state in here, but it works on what they call piezoresistive. Semiconductors change their characteristics depending on compression. Now, carbon is really, really, really good example. So carbon, the more you compress carbon, the less resistance it has. The less you compress it, the more resistance it has. Originally, when they came out with regulated power supplies, they used what they call a carbon pile regulator. And you might run into one of those out there. So what they would do is if your voltage it had a solenoid on one side pulling against a carbon pile, so a bunch of carbon discs. And what would happen if the voltage started going up, the solenoid would pull back. It would make the carbon pile have more resistance, which would cause it to go back down. If the output voltage of your generator tried to go down, then the solenoid would lose pull. It would come up here and compress them and cause the resistance to go down. So carbon pile regulators were around a long time before solid state regulators. So pressure sensors. Do you think we got pressure sensors on our line? Okay, so let's go